Let the birds sitting.
A very warm afternoon to one and all present here. I wish you all a very see a lot of faces. Welcome you all to the 10th talk of the seminar series of early academia and industry exposure for students. It gives me great pleasure to introduce you all to our speaker for the day, Dr. Rigler. She's an industry professional from Maggie Scientific, right from his graduate studies. He has been working closely in the field of laser and optical engineering. He obtained his Bachelor of Science degree and PhD, both from the University of Louisiana. Post completing his PhD, he has been working in the field of aerosol science and measurements. In particular, he has been working on the measurement techniques related to carbonaceous aerosols. He has also published his works in various reputed international conferences. Currently, he is working as the head of the R&D manager of the Total Carbon Analyzer at Aerosol TO. He'll be delivering a talk on the same today, titled High Time Resolution Carbonaceous Aerosol Fingerprinting using total carbon, black carbon, CASS method. Without further ado, let's welcome him on the dais, Dr. Rigler.
Okay, is it good? Yeah, first of all, thank you for the nice introduction. I'm really honored and happy to be here and having opportunity to present our work. So today, like it was introduced, I will talk about multiple phases of carbonaceous aerosol. So in focusing on high time resolution fingerprint using the advanced TC-BC method, which was developed within our department. Of course, this is not only my work, it's work of many people involved, especially Matits in ASTA, which are my colleagues in the department. I will just start briefly with introducing our company, our department. So we're coming from Slovenia, Ljubljana. This is a small country, only 2 million people of population. So it's somewhere in the Central Europe between Italy, Austria, Croatia, and Hungary. We are a partner company of Maggie Scientific, and since 2007 and many years before, even we are working on instrumentation development for carbonaceous aerosols. So focusing on the R&D department, there's 12 of us, which is somehow, I would say, unique for the private company. 6 of them are having PhDs and working really on basic research, and another 6 people then working on development. So all of the instruments that I will show were developed within our group, all of the methods also. So, you know, from the basic idea on the paper to the final commercialized product. So this is something that we are really proud on. And today we'll talk about 2 products, actually method using these 2 products. So one is a thalometer A33, and the other one is combination of A33 and total carbon analyzer, which we call it the CASS, so Carbonaceous Aerosol Speciation System. So to start with the introduction, carbonaceous aerosols in general are extremely diverse. So on one hand, we have black carbon or elemental carbon. Probably you are very familiar with it. So it has really known chemical composition, more or less just carbon. And the special property of it, it's strong optical absorption in the whole wavelength range. On the other side, we have organic aerosols, which consists of, you know, different molecular structures. So it has to be carbon, but then it can, you know, other atoms like hydrogen, oxygen, nitrogen, sulfur. So this is a group of very complex and different chemicals and aerosols. And unfortunately, this organic aerosol fraction is on one side the largest, but also the least understood one. To deal with the terminology, when I'm talking about carbonaceous aerosols, I'm talking about the sum of black carbon and organic aerosols. So organic aerosols is actually the mass of the whole aerosols that include carbon. And when I'm talking about the mass of carbon atoms, I'm talking about total carbon. So this is the mass of all carbon atoms that can be found in carbonaceous aerosols. So BC equals BC, more or less carbon. And organic carbon is the carbon part of organic aerosols. And to continue with the motivation, there are 2 really, you know, important publications in 2021. One is World Health Organization, which again recognizes carbonaceous aerosol and especially black carbon to have a big impact on public health, and also IPCC. Again, confirming that black carbon, you know, is the second contributor to global warming, but also that people should measure carbonaceous aerosol as well, because there is a big uncertainty on how they impact climate. On one side, you have this absorbing part of organic aerosol called brown carbon, which contributes to the warming, while the non-absorbing part contributes to the scattering of light, which of course at the end makes cools the environment. So this is our collaboration with Helmholtz Dresden Institute in Germany. And this is the filter tape that is used in our instrument, the thalometer. And if you use this is helium ion microscopy pictures, you see that how irregular the shape of black carbon is. So it can be really small. So these small fractions of a few nanometers on 10 of nanometers, which can then condense together to get a really big and strange particle. So being so small on one hand means that they will come to the deepest, so that they will come to the deepest sides of our lungs and then even to our blood system. But having this large specific area, it means that there is a lot of potential, a lot of area where organics can stick on. And so they're really good transporters of toxic organic material into our system. So in our group, we are mostly focusing on carbonaceous aerosols. We are doing many, researches. Today I will more or less talk about the source and component apportionment, We are also doing emission factors of black carbon, production of black carbon, connection to the meteorology, and so on. As sources go, black carbon, fortunately, black carbon is only primary and quite inert in the atmosphere. So it's emitted by the incomplete combustion of carbonaceous fuel, and most two sources are important. One is traffic, so internal combustion engines, and on the other side, biomass burning. They make totally different properties of black carbon, but these are the two most significant sources. While organic carbon, it's emitted as a primary organic matter, either again by combustion or some biogenic processes. What is also important, and what we are focusing in what is, let's say, a hot topic in recent years, is this secondary origin. So once you have these gases in the atmosphere, which are emitted with the primary emissions of organic matter, with the right, let's say, ambient properties, energy coming from the sun or other precursors, this gas to particle conversion can happen. So then you can have at the end a huge amount of secondary organic particles, which contribute to PM2.5 mass quite significantly, as I will show you later in my talk. So this is then the schematic view of how carbonaceous aerosol look from the source point of view. Black carbon, so these are these inert black particles, which usually comes from either traffic, biomass burning for household heating, or wildfires. Of course, coal burning is also one of the sources, industry, and so on. Then it's primary organic aerosol, again coming from these sources, but also from biogenic emissions. This is also primary. And then a big chunk of mass of organic aerosol is a secondary form. So there are millions of pathways. I will, to simplify today's talk, I will more or less concentrate on these two. So one is photooxidation. So photooxidation of the precursors that are emitted either via traffic or biomass, or this night formation of secondary brown carbon. Okay. So why the title multiple phases? Actually, we look at the carbonaceous aerosols from two directions. One is if it's primary or secondary, and the other is their optical properties. As we know, black carbon is really a strong light absorbing part of carbonaceous aerosol. Also, this brown carbon recently became very important as far as climate changes go. And there is this non-absorbing part, so transparent particles which scatter the light. So why do we need this separation? This motivation for that. As I said, black carbon has a great effect on the public health. It's a universal carrier of wide variety of chemicals of varying toxicity to human body. And it's really strong absorber. So from ER to UV, strongly absorbs light, and by that warms the environment, so air and atmosphere. Brown carbon, as public health effect goes, polycyclic aromatic hydrocarbons are major, constituents of combustion, and they are highly absorptive. So the toxic part of organic carbon usually hides in brown carbon fraction. And also because it absorbs light, especially and better at the UV region, it's also a climate forcing agent for the global warming, but of course with greater uncertainty than black carbon. And organic aerosols that don't absorb light, they're scattering. First of all, it's the largest fraction of PM2.5. So, if you want to reduce PM2.5, this is also the fraction you need to look at. And because of light scattering, they contribute to climate cooling. So how we measure and how we distinguish or apportion different fractions of carbonaceous aerosols. On one side, we are looking at the light absorption, and we are doing that at many wavelengths from ER to UV. And on the other side, we are looking chemical refractiveness. And this is because more the particles absorb light, more they're black, more refractory they are. So it's harder to, do anything with them. And more that you go down with light absorption, less refractory, more volatile organic species you will get. So this is where the idea of our instrumentation comes. These are the thalometers. They measure light absorption of aerosols that are sampled on the filter. While the CASS system is a combination of A33 and total carbon. So total carbon measures the whole, so the whole amount of carbon that can be found in aerosols. And if you combine those two measurements, you can actually get those speciations that I was talking about. I know that you are pretty much familiar with the old A31 model. So this is the next generation. I think we introduced it in 2013, I think. So the principle stays the same. You have inside the instrument, you have a white filter tape. The pump sucks air through the filter, and within the filter matrix, of course, gases go through, but the particle gets stuck on the filter fibers. So every second above the filter, we have a light source, and we shine the light on the filter, and then we measure how much of the light is transmitted through the filter material and the aerosols that are on the filter. And if you combine this with the reference measurements of the white spot of the filter, you can get attenuation. The attenuation is the name of light extinction on the filter. This is quite important. So, in the ambient air, you have light extinction because of the scattering and because of the absorption on the aerosols. On the filter, the things get a bit more complicated. Because of the filter fiber, you will get additional scattering because of the filter fibers, but you also get this loading effect, of which I will talk a bit later. So once you have the attenuation, you can calculate the attenuation coefficient. So this is flow area. And because we are doing this every second, we are actually measuring not attenuation, but derivative of the attenuation. So every second, we measure this. So the attenuation coefficient is actually proportional to derivative of attenuation. And then, when things become complicated, is how to convert attenuation to absorption. There are two things that you need to cover. One is MEC, which we discussed earlier, and the other one is this multiple scattering parameter. So this multiple scattering parameter is a function or a property of the filter, but it can also, so the scattering aerosols that are on the filter can also influence this C. So it's important, and there are some assumptions. Doing that, we are assuming low single scattering albedo, which in some cases is true, in some cases it's not true. So this is something you need to take into account. If you do this at many wavelengths, you can assume this angstrom exponent function. And this can be then used for source apportionment. So loading compensation, so this is, I think, general property in physics. When the spot becomes darker and darker, you're actually losing the sensitivity of the instrument. So the attenuation, at one point, the attenuation, if you would imagine graph of, having here the black carbon concentration and the attenuation, at the beginning it would be linear, but then it would separate. Okay, because you have more and more material on the filter. So clever idea at the time, and which is also patent, is this dual spot algorithm. So we are not sampling only one spot, but two spots in the same time. So one with a higher flow and one with a lower flow. The aerosols are the same, of course. So the loading properties are the same. So actually, at the end, you get two equations with two unknowns, and you can get this K parameter. So this is loading compensation coefficient, which tells you how to compensate for this loading. So instead of getting these jumps when the filter advances to a fresh spot, you actually can have continuous measurement of black carbon in real time. Okay, so now the source apportionment. Because we are measuring at several wavelengths, so it's for the A3387 wavelength from 370 in UV to 950 close to ER. You can actually apportion the black carbon at 880. So the black carbon is defined and measured at 880, but looking at this angstrom exponent coefficient, you can distinguish between black carbon, which is really fresh and black and coming from traffic, in respect to black carbon, which comes from biomass burning. So this is the fraction that's usually coated with organics, and this fraction will absorb more in the UV region. So having this equation, assuming angstrom exponents for fossil fuel or traffic and biomass burning, you can actually get in real time how much of your black carbon at 880 comes from either one or the second source. But you can take this even into a higher level. You can, do source apportionment of black carbon, but you can also look at what's going on at the curve here. And, assuming that all the things that are absorbing at 880 is only black carbon, and then black carbon has through meat theory has the angstrom exponent of 1. So if you extrapolate this exponent of 1 here and you subtract from the whole absorption, you can actually detect how much of the species absorb in the UV, which is not black carbon. And this piece, so this brown chunk here, I mean, the equations are a bit more complicated, but at the end, it's quite simple. You can detect how much of organic species absorb. And if you know the right MEC, and this is where the biggest uncertainty comes, you can actually determine the mass of brown carbon. So the organic aerosol part of organic aerosol that absorbs light. Okay, so this was a thalometer. If you have any questions, please let me know. You can, of course, ask me in between. Now going to the next one. So total carbon analyzer. The basic idea was, let's have the OC and EC measurements or OC and BC measurement in real time in high time resolution, but without using any gas, because the standard way on how to measure OC and EC is with these OC-EC analyzers, which use helium and helium plus oxygen purity gases. Here, the idea is much more simple. So let's have one instrument that measures the total carbon. And then if you subtract the black carbon, which is measured by a thalometer, you can, in real time, get organic carbon. So how do we do it? Principle of operation of the total carbon. When you open the door, you will see two chambers like this. In each of the chamber, there are two heating models. One is below and one is above the filter. So here in between, you place the filter. It's quartz fiber filter. And when the aerosol are being sampled on the filter, then you stop with the sampling and you turn on both of the heaters at the same time, and you bring the temperature in really short time up to 950 degrees, and more or less all the carbonaceous aerosols are converted to CO2 because there is oxygen present from the ambient air. You have high temperature, and you actually vaporize all the carbon from the aerosols to CO2, and then you measure the CO2 in the end. So the schematic view of the instrument looks something like that. So when one chamber is sampling, the other one is doing the analysis, and when the analysis is finished, the instrument just changes. So now this filter is performing analysis, sampling, and this one is performing the analysis. And this can be done because after the analysis, after you burn everything on the filter will be white again. So you don't need to change filter every time. So you can just leave it in the instrument for 2 weeks, 3 weeks, and so on. And when you burn all the material, you have you get a plume or peak of CO2 above the ambient CO2 values, and you take it to the CO2 sensor. You measure the area of the peak. Then you convert it back to how much of the carbon was on the filter. Okay, so now we have BC. We have BC at multiple wavelengths, with which we can distinguish between fossil fuel and biomass black carbon, and we can also determine the brown carbon. And we have TC. With TC, go back. If you assume or determine the OA to OC factor, so the difference in mass of carbon atoms and the whole organic aerosol, you can get the mass of carbonaceous aerosol in real time. So this is actually the umbrella or the limit, the mass closure that we use for all the carbonaceous aerosol. Okay, so now I will talk about actually one study that we did, but 2 papers are also important. So this is what we published in our group. The first one, so this is from Luca paper, is about the A33. The second one is about the total carbon, and then the third one is the new method that we developed. I think this was published last year, and it goes like this. So when you measure the TC and BC on high time resolution, by high time resolution, I mean every half an hour, because a thermometer works on 1 minute time resolution. The TCA works on 20 minutes, half an hour, 1 hour, so it depends on the concentration. You can actually get the whole speciation or the whole fingerprint of carbonaceous aerosol. So at the end, you have 6 components. You have BC from 2 sources, then you have secondary organic, which absorbs light, so brown carbon, secondary brown carbon, secondary non-absorbing organic aerosol, primary non-absorbing, and primary brown carbon. And this is done by using all of these 6 numerical models. So I discuss source apportionment of black carbon. I also discuss brown carbon determination, and then this is called a BC tracer model. So when you have OC and BC concentrations on high time resolution, you can run a BC tracer model which searches for the OC to BC primary ratio. And it searches it in a way that there is a good correlation between primary OC and BC, and let's say the worst correlation between primary OC and secondary OC. And you can do this algorithm if you have a lot of data. And then you can calculate this primary to OC ratio. I can tell you more in following slides. Okay, so this method was developed in collaboration with South Coast Air Quality Measurement District in LA, Los Angeles. So this is Southern California. We had 2 stations here. One was in the center of the city, and another one called Riverside was more east of it. And we chose these 2 locations in a way that this was the source site. So this is where all the emissions came. And because the winds during the day goes like this, so they are diverted by this mountain ridge here, this is so-called receiver sampling site. So whatever is emitted here, this site will get it. So we can then compare these 2 sites for the fingerprints. This is 2 years of data, TC and BC, and more or less full data set. And these are just the first diurnal profiles for different seasons, so 2 seasons each for both sides. And what is interesting, so the black one is black carbon, the violet one is the TC. What was interesting that in the middle of the day, when the, this is morning rush hour, BC goes up, of course, TC goes up because OC is also emitted. But when BC goes down, and it goes down because the boundary layer goes up because there are high winds, you have the sun energy, so you have the warm grounds. So the boundary layer goes up, and you should see the decrease of all pollutants. But you have a big peak that is, that has a peak in the middle of the day of TC. So this is, of course, secondary formation, and it's, if you look it in the eyes of the production, it's impressively big, so it's significant. So for this, we then did all of these steps, and at the end, what we got something like this. So this is working day, Saturday, Sunday, all seasons for both sides. Okay, and what you can see, I'll just go through some interesting events. Summer, especially summer, you see there is no big difference between working day and weekend. What you see is this peak, which is secondary non-absorbing organic aerosols. And the pathway for this is all the precursors, all the gases that comes from traffic. And, I must stress out that in LA, specifically, more or less the whole vehicle fleet comes from petrol, not diesel. Diesel is only for the trucks. So there is a lot of organic precursors emitted in the air. And when the sun kicks in, you get this photooxidation, you get this vast production of secondary organic aerosol, which is transparent. While the black carbon, follows the regular traffic pattern, and also the primary organics which are not absorbing, and this is something that we know is true, follows this. While in the winter, especially in the weekends, they are using also wood for either household heating or recreational burning, picnics and everything. So the difference is that there is no peak of secondary in the middle of the day, but in the evening, you see there is a small brown fraction of black carbon. That means that they're using biomass as a fuel. But what happens also during the night, the precursor that comes from biomass burning, so this is one of the possible pathways, but we think is the right one, is known as catechol. And when you also have the presence of NO3, and in the night, so this pathway favors the high relative humidity, which of course happens during the night. You have the production of this secondary brown carbon, which was also confirmed by other studies. And, we saw it in real time, which we are really happy. And then for the riverside, things look similar, but there is the fraction of secondary is even higher because the aerosol had time coming from the source region to the receiver region to get, to having this secondary aerosol coated on the primary particles. So this fraction is then even higher. And this is nicely seen in this fingerprint, we call it. So how the pollution rose of carbonaceous aerosol looks like for the certain location. And you can see that there is more secondary organics in the riverside in respect to central LA. And you see that there are small amounts of biomass burning as well, but mostly it's non-absorbing secondary organic aerosol and non-absorbing primary. What was really funny, and that was the reason for our second study, if you look day by day, in California especially, there is a lot of wildfires. So this is one of the, let's say, consequences of the global warming there. The land is really dry, the forests are dry, so there you have a season of wildfires. And if you look data day by day, you see that this pollution rose completely changes, of course, when you have the plume of wildfire coming to your station. So then we, in the second study, we more or less focus on this. So we had, again, these two stations here, but one more in Berkeley. which is, traffic site. So it's a big highway, and there is this sampling site. And what happened? Unfortunately, but lucky for us, there was a campfire event here. This is close to the Paradise City. I think it was the largest and most destructive fire in California history. And when the fire started, in 2 hours, the first plume was here. So it takes 2 hours for 200 kilometers. So we really got fresh emissions from the this wildfire event here. And this is, back trajectory, which was done by my colleague Matic, back trajectory analysis, coupled with the satellite images, coupled with this, low-cost purple air sensors of PM2.5. So you can see that everything really correlates with each other. So we did a similar analysis. You see, before the wildfire, what you have is this typical diurnal profile of traffic: morning rush hour, then dilution because of the boundary layer gets high, and then evening rush hour. And this happens every day. Not so interesting. But when this happened, you see that concentrations, especially organic carbon, skyrocket. You cannot see, I mean, there is also a lot of more black carbon, but where the mass, PM2.5 mass comes, is the organics. So we separated the fire into 2 phases. First one was these fresh emissions that came directly to our station, and it was more or less active combustion, so acting fire of the fuel. While then the second part, the fire was more or less smoldering, so it was not all the vegetation was combusted in the first phase. So more or less there was smoldering, but a lot of mass of carbonaceous aerosols. So, after during the fire, the BC went up for 4 times, but OC went up for 12 times. So this is where all the PM mass is actually hidden. We did the same analysis as before. So this 6 component fingerprint, and you clearly see Y2 phases. The first one, because it was active, the aerosols didn't have time to age, didn't have time to be coated or to be changed in the air. So what we see is more or less BC coming from biomass, some of primary OC, which is transparent, and a lot of primary brown carbon, which is, of course, the coming from biomass. And then in the second part, which was more or less smoldering part, you see that now these air masses are moving more slowly and they have time to age. And that's why we are also seeing secondary brown carbon and secondary non-absorbing organic aerosols. But looking at the brown carbon apportionment or brown carbon fraction of absorption, you see that it's really it really pinpoints when the fire happens. So then this gives us an idea. Let's draw brown carbon fraction of absorption in this way. So this is for the whole measurement campaign. This is months, and this is day of the month. And you can really pinpoint different wildfire events that happened. Of course, you have this winter pattern, which you'll get a bit of brown carbon from household heating, but you really have these points which were all connected to the different wildfire that happen nearby or not so nearby. And this is the same for the riverside. So the one was in the north of California, and this was the south. So we could all connect our brown carbon measurement with wildfire that were found on Wikipedia. Okay, so this is now the last study that we did. This was done in Paris. What we wanted to do is compare this method to the ACSM. I don't know if you're familiar with the ACSM. So this is aerosol chemical speciation monitor. It monitors, I can show you here. So it monitors different online and in real time different species of aerosols. So organic aerosols, which is similar to what we are doing, but there are also other, like sulfates, nitrates, chloride, and using the PMF or doing a PMF on this data, you can do some sort of source apportionment with ACSM. So what we wanted to do is connect our measurements to the ACSM, which is, to validate it. And this ACSM is quite well known and well validated with other techniques. So we had two CASS system, one in PM1 and one in PM2.5. The thing is that ACSM only works with PM1. So it has this aerodynamic lens, which somehow allows only PM1. The newer versions also allow for PM2.5, but they're not validated yet. Some discrepancies were showed in last years when they were doing measurements with it. So most of the things is still done with PM1. So again, this is what 1 year campaign in Paris. So this is suburban part of Paris, south, 20 kilometers out of the center. So PM2.5, PM1, and ACSM PM1. First of all, what we could do is measure the OA to OC ratio. This can be done now, before it was assumed here we could measure it. And it was quite high, surprisingly high for us. So this is OC from, TC minus BC method versus OA from ACSM. The correlation is really good. And it's not really changing from spring, summer, and autumn, which is also good, but a bit surprising. And it's quite high. So this is, 3 point something, 3.9, 3.1, 3.3. Okay, so again, we did this analysis. So similar things as we saw in other similar, let's say, locations. And now this is the direct comparison of what we are seeing with our method and the ACSM method. So we have black carbon, primary organic, and secondary organic, which then equals to what ACSM is measuring, or what PMF is giving us is this fresh organic aerosol, HOA, and BBOA. So this is primary, coming from two sources. And secondary, in the, let's say, PMF terminology, this is called low oxidate OA and more oxidate OA. So what we're at the end really happy if you put this on the same plot, we are really happy that what we are getting with let's say much simpler method is really similar to what they're getting with ACSM. So about the same ratio of BC, of primary OA and secondary OA. With that, I would like to thank you for your attention. If there are any questions, please let me know. Yeah, so yeah, so yeah. So how exactly the PMF works or how they did it, it's unknown to me. But actually what you take several signals of OA, like you say, this M to Z ratio, and then you put it into PMF with all the other measurements that you have, and by that you determine this how oxidated the organic aerosols are. But this is the things that were done by our partner in Paris. So sorry, I don't have any details on that. Yeah. 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 Yeah, this is something that was also, this OA to ratio change on the source. So if you have fresh, let's say, emission from traffic, roadside measurement, it was believed that OA to OC ratio should be something, 1.6, 1.8, something like that. When you have aged aerosols and when you have a lot of biomass burning, this number will get higher. But we believe that this number is about 2.5, which, when you get sources, and you must know that in winter and autumn, there is a lot of biomass burning for household heating also done in Paris. These plumes have time to age coming here. So I think, and they're getting, more oxidized. And this is the thing I would, I would say that's the reason that we get so high numbers. But it's still a debatable thing, because I mean, from the papers, scientific papers, this should be more, from 2.5 to 3, not more. So this is something that we're still investigating, yeah. And we didn't publish this yet.
Hello.
Yeah.
I think follow the BC also is in April, you can see the rise.
Yeah. Aha. You mean like general BC pattern? Yeah. This is more or less connected to the meteorology. So if you have, if you have wind blowings, again, it depends from, where the wind directions of the wind. So if you have wind blowing from the city, you will get higher concentrations. If you had winds from the west, which also happens quite frequently, there is seaside, you will get, decrease in concentration. But one thing that is also important here is that you see that PM2. If you look the difference between PM1 and PM2.5, you see that you get more OC. So what we think is happening that when you have this secondary condensation on the existing particle, this particle will get even bigger than PM2.5. So that's why part of mass or part of organic aerosol you are actually missing with using only PM1. Yeah.
He has to be 370. The previous slide.
Which? This, yeah.
370.
It's 370, yeah.
And the ground power 470. And we're doing the instrument experiment.
So for brown carbon, we are using all 7 wavelengths. Yeah, this BC apportionment for this, we are using 2, like you said, the ones that you are using. But for brown carbon, we assume that at 950 there is no absorption of organics, and then we extrapolate the function, the exponential function with angstrom exponent 1, and then we fit whatever we measure with different exponential function. So this is fitted on all 7 wavelengths. And then the difference between is what we determine as brown carbon. Yeah.
Hello.
Maybe one thing, but it's not yet, official. It's quite interesting if you look these patterns for different cities, and you see, well, once you reduce primary emissions, you will still have quite a lot of secondaries. On the other side, if you look, for example, this Shanghai from China, you will see that, measures should be done on primary emissions first and then on secondary. So you can really see the difference.
Hello. Hello.
Any additional possibilities are met.
Oh, can you repeat the question?
Two versions of this kilometer.
Yeah.
Compared to thermal
Is it like having few more better? Way it operates it.
By so by different version, you mean 31 to 33 or the OCEC?
Yeah.
Yeah, so let me go. Yeah, okay. So BC and EC is the same thing, but it's measured in different ways. Okay, one is optically, and when you measure it, is EC is thermal optically. Right? So for this and for this LA, we compare our BC measurements to the EC measurements that were done at the same sampling site. So they sampled filters every 6 days and then used the improved thermal protocol, and we got really nice one-to-one slope. But what I want to say is that when comparing EC to BC, first of all, you need to take into account which thermal protocol is used. So is it NIOSH, is it improved, is it USOR, what we use in Europe? And on the other side, also BC measurement, as you know, can be affected if they're coated. You are studying MEC and so on. So what we really somehow suggest is to do a collocated measurements for one place, for several seasons, and then have this comparison slope between BC and EC. But what we think and what we strongly believe, you can get much more data from having high time resolution BC measurements. Every minute you can study diurnal profiles than having one 24-hour point from EC. But to fulfill the standards, we somehow, and this was also presented in my paper, so about the TCA, we somehow, let's do a collocated measurements of filter sampling and BC measurements, and then see what's the slope. Because both, thermal protocols will influence and sources will influence on this correlation. Yeah. But in this paper, and if there is interest, I can share it with you. In the supplement, we really did validation for all of these measurements, and one of them was 2 years of BC measurements versus also EC measurements. Yeah.
Hello.
Let me the difference in primary and secondary.
That's a good question. I didn't want to go into details, and all the details are again in the paper. I have one supplement slide, which get a bit tricky. So this is calculated like this, and what's the beauty of it is that this OC to BC primary is not assumed, but it's calculated. So what you do, you take different OC to BC primary. So you guess different OC to BC primary ratios, and you put it on the x-axis. And now you look the correlation to, so by this formula, you look correlation to BC. So primary OC must be well correlated with BC. This is the first assumption. So when the correlation of primary, this guessed primary OC is good with BC, and at the same time is the lowest for the secondary organic aerosol, this is your primary OC to BC ratio. And having this, then you can calculate everything. So, OC you measured, POC is actually your OC times minus OC to BC primary times BC, which is also measured. Then you have everything. Yeah. But what is needed here is long-term data set where you can put all of this, frequency diagram, and then you can calculate this. So again, what we suggest here is before, you cannot just put this instrument there and it will start showing the right result. You should do, first of all, like a campaign like that, and then you determine all the factors, and then you put it, and then it will show you in real time. Yeah. Different structure, yeah, yeah, for sure. Secondary organic will be more volatile than primary, for sure. So it has different, it has different POC to POA ratio, and secondary are more oxidized. So this POA to POC ratio will be different than SOA to SOC ratio. Yeah, I know. I mean, there are thousands of molecules that form secondaries and primary sources. So, like physically, you won't see any difference. I mean, under the microscopes. But the secondary for sure is more volatile. Yeah. So this is where you can start looking. Yeah. But millions of different molecules and structures. Yeah. Because this secondary can be formed directly from gases. So this is one. So it will start like this banana plot, if you're familiar with, or it can condense on the existing particle, and even this will change the structure. Can you repeat the question, please?
We do something.
Yeah. So it's actually a good question. This is something that we noticed. So now in last year we had some chamber experiments, and we noticed exactly that. So when they were formed from gases, they were really spherical, really spheres. While slowly condensing on the existing BC particles, it was like coating. So it was not really, it was irregular shapes. Yeah. So this is one of the things that we noticed. Yeah. But we try to, at the end, we still try to focus on the optical properties. So this is something that is not really my field. Yeah. 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 Could distinguish between those two. Yeah, you're right. Yeah, you're probably right. Yeah.
During the cyclical variation, we need the more because actually is able to might be a little bit of variation in the elevation. So we expect the same kind of trend in this
Which back? Different seasons. Okay. This, yeah.
Is there a delay between the peaks of battery and compound and the how primary and secondary is
Yeah, okay. This is something that I don't have a lot of experience with. Yeah, with rainy seasons. But I mean, what we notice here is the primary exactly follows BC pattern. The primary emission. So also the primary organic carbon, and this is how the model actually works. And the same goes here. While for the secondary peak, it really depends on many parameters. One of them is, of course, you need sun energy for the photo oxidation to kick in. So that's why it happens when, you know, the sun is the highest. So if you would have a rain, that would of course not happen, and you would wash out this. You wouldn't see this peak, I guess. Yeah. Yeah. This? Winter, yeah. Yeah, it's not only sun. It's not only sun. Yeah. No. Like I said, there are many pathways for secondary aerosols, but what is really, what is really interesting here is you must know that in the summer, when the sun shines, the planetary boundary layer from 1 kilometer goes to 10 kilometers. So there is a lot of volume to mix the particles and a lot of volume for dilution. And if you see peak like that, that means that the production must be enormous. And this pathway, we believe, is through photooxidation. But there are other pathways that don't need, you know, direct sunshine for these secondaries to be formed.
Thing is, yes.
Thanks, Marty.
Thank you.
We have participants and also online. There are few participants and also online. We have got all, including IST management, for this wonderful talk. And as a token of appreciation, we have a small IST mug. So, we request HOD to set out to present at least 10 minutes. Very nice.
Thanks for thanks for all the questions.
Very cool.
Thank you.